What's up, team? Today we're going to discuss one of my favorite topics in the whole course. We're going to talk about proving two triangles are similar. First, a little bit of background. This next piece won't be on the exam, but it'll help you just bring a little bit more understanding of the topic. So in about 300 BCE, Euclid of Alexandria, you hear me talk about him all the time, he published this text called the Elements. It's 13 books, and it's a collection of proofs. And his proofs, they started with a basic underlying what he called axioms, or what we call axioms now, which are these agreed upon truths, such as a point is a point, and if you have a second point, you can connect them with a line, right? So just basic stuff that nobody could argue against. And from these basic facts, he built all these just wonderful, beautiful truths that can be reduced down to these definitions and axioms. So in his text, I always have these in my classroom for the nerds who want to check it out. But you can see it's this English translation that came out in the 1900s is pretty technical, lots of words and symbols and whatnot. His wasn't quite like this, different language and 2,000 years of a culture gap and whatever. But this is how we read it today. There are other variations. For example, this one's all built with colors, and notice how there's no numbers or letters in this. It literally just says things like the yellow angle and the red angle, and it talks about them that way. So easy to understand if you read it from scratch and have patience to dig through it. So if you're ever curious, I always have those on my bookshelf in my classroom, but that is not what we're going to be discussing directly today. Today, we're going to just introduce the concept of proof, what it is, how we're going to approach it in this course. Again, in classical geometry, it's all proof-based, whereas what we're doing, we just touch on proofs ever so slightly. We focus on the computational side of things in this course, really in geometry in this country. So a proof in general is just a logical argument that demonstrates some sort of truth. You've heard it, in real life outside of math class when someone says something and you're like, hey, prove it. Like, well, okay, let me present my arguments for you. This is why X, Y, and Z is true. And then you can either choose to follow their logic and be like, yeah, that totally makes sense. Or like, hey, no, I see what you're trying to do there, but did you think about this scenario? And you might provide a counter example or whatever the case may be. So a mathematical proof is, it's foolproof. Like you cannot poke a hole in it. And if you can poke a hole in it by providing a counter example of some sort, then it is not true. So we're going to practice this skill, and the arena that we're going to practice it in is with these similar triangles. So we've talked about this similarity criteria. This is from a prior lesson. I'm not going to teach what these are right now. If you're not familiar with what side, angle, side, and angle are, or what those mean, please check out the previous video, the previous note set. It's all there. But we're going to use these ideas that we've discussed previously to complete a proof. Now, before we do this, there's a little bit of background. There are different ways to present a proof, lots of different ways to present these arguments. Formally, you might see some two-column proofs. You might have heard of those. We're not necessarily going to be approaching those this year, although I'd be happy to chat about them with you. Sometimes you have proofs in paragraphs, like when I was in college, when I was wrapping up my undergrad. Everything I did was on a computer, all my math class, and I had to type everything out with all these fancy symbols, and there's fancy software and all this type of stuff. We're not doing that either. There are picture proofs, so we can literally just draw pictures and that would tell the story, where you'd expect the audience to be able to follow what's going on, and you can prove some things. There's a really cool proof of the Pythagorean theorem just using pictures, which will probably explore in class at some point in time. Another popular form of proof that's a bit more accessible to just I don't want to say anybody, but most folks, and that's the one that we're going to pursue in our course, is flowchart proofs. So we're going to show some certain things, and then the flowchart is going to point to the next stage of the proof. By saying like, hey, because this is true, then this other thing is true. Because this thing is true, then this other thing is true, etc. So let's do one example of these. This is one of the examples that's in my note set for this lesson, and I'm just going to walk through this one from scratch and kind of explain my thinking. And from this, if you're able to follow, you should be able to follow the other examples in the note set as well. So prove that triangle ABC is similar to, that's what the single squiggly means, triangle DEF. Okay, well, let's get our bearings a little bit. I'm seeing triangle ABC, I'm seeing triangle DEF, and I need to take into account what information is given, and then from that, am I able to use one of these criteria to prove that they're definitely similar? So before we even start writing, let's make a game plan. I'm noticing that I have 3 side lengths here. They're 8 and 10 and 12, and here I have the side lengths of 16, 20, and 24. Okay, this one there's a little bit of low-hanging fruit. So we know that we have the three sides, so we're probably gonna end up using side, 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 right? We don't have any angles, so we can't use side, angle, side, and we still don't have angles, so we can't use angle, angle. So if anything is gonna work, it's gonna end up being side, side, side. Now let's remind ourselves, what the heck does this side, side, side criterion need in order for us to utilize it? Well, we need to show that all three sides are proportional to one another. All three sides are proportional to one another. Meaning we need to show that DE is to AB. They have the same relationship as DF has to AC, which also has the same relationship as BC to EF. So if we can show that, then we're in a really good spot, but we have to spell it all out. You might be sitting at your computer screaming at it, be like, hey, there's a scale factor of 2, it's obvious. Yeah, it's obvious to me too, but we need to spell it out with logic. We need to spell it out as though our audience doesn't see that it's obvious. So what we're trying to show is that, again, AB over DE equals the same thing as BC to EF, which equals the same thing as AC to DF. Okay, so we got to show all of this, and then that'll lead us to our conclusion. So let's explore. What is AB over DE? Well, AB has a length of 10, and DE has a length of 20. Okay, so here there's a ratio of 1/2. Okay, fine. Let's look at this next one. Let's change colors here to kind of differentiate here. I'm gonna look at BC over EF. So BC over EF, just doing a little bit of exploring now. BC has a length of 12. EF has a length of 24. That can also reduce to 1/2. Great. Let's explore AC. I'm gonna do it up here just to have a little bit more room. AC has a length of 8, and DF has a length of 16. That also has a ratio of 1/2. Okay, hopefully by now, if you were unconvinced that these three pairs of corresponding sides shared the same ratio, if you were following along and understand, how to simplify fractions and how to identify the sides, so there's some common notation here we need to be on the same page with. But if you were able to follow along, there is no doubt that all three sides here, all three pairs of corresponding sides are proportional. They have a ratio of 1/2. Well, because of that, that satisfies the side, side, side criteria. That demonstrates that these are definitely similar triangles. So we can now draw a conclusion by saying triangle ABC is similar to triangle DEF because all three pairs of corresponding sides are proportional. Now we don't have to spell all that out. We can simplify it and just say because, and we can extra abbreviate, because SSS, because of side, side, side. So the flowchart element of this proof is that there are three components that we need to demonstrate to say that this is definitely true. The first component is here, the second component is here, and the third component was up here. So again, to recap, we were given these triangles. We were not told that they were similar. It was our job to demonstrate that they are definitely similar. That's the crux of what a proof is. So we need to state our goal. So our goal was to demonstrate that these are similar triangles. Again, if you're not familiar with what a similar figure or similar triangle is, check out a previous video, I explain it. So we took into account what we had. We had the lengths of all three sides of both of the triangles. We then observed, hey, I think these are all proportional, so we're gonna use side, side, side. And then we actually had to spell it all out. We said, hey, we're trying to show that this is true, and here is us doing it. The first pair of corresponding sides, they have a ratio of 1/2. The second pair of corresponding sides, they have a ratio of 1/2. Same with the third pair. Because they're all the same, because they're all 1/2, well, then they are all proportional, and that information leads us to the facts that this is true. So in these bubbles of our flowchart, we have to tell part of the story. Each bubble has to have some component of truth that applies, that we're going to use as information in our proof. Here, the piece of information is I'm saying, hey, these have a ratio of 1/2. That's not enough to tell the story, but I'm going to combine it with more information. I'm combining it with the fact that this pair of corresponding sides also has a ratio of 1/2, as does the third pair. So it's 3 separate pieces of information that alone mean nothing, but together really paint a beautiful picture by saying, hey, these triangles actually are similar because of the side-side-side criteria. Okay, here's a real basic proof of how to demonstrate 2 triangles are indeed similar. Check out the practice problems. There are more questions. Please ask. You got this.